Welcome back. This is the Tutor Wizard. Please subscribe right here. Hit the notification bell. This is Alice. I'm Adrian. This is Noodles. We're the Tutor Wizard. What we're going to do today is a history of mathematics. Congruence modulo M is essentially what we're going to do specifically, but we're going to break this into probably 2 or 3 videos. This lecture specifically what we're going to do is the definition of congruence mod M, some basic modular arithmetic, and some results about congruences which will help us compute the black magic, which is modular arithmetic base M. Let's get to it. All right, congruence modulo M greater than or equal to 2. What we're really doing with this is we're going to fix an integer. Let us run with 5 for the next few scenes. What we want to do is fix a number 5 and divide everybody else by 5. So in particular, what we're going to do is we're going to take, say, 2 integers a and b, and we're going to compare them with respect to 5. Not whether they're equal or not, but we want to know if they're congruent or similar or the same with the measure modulo m equals 5 or m greater than or equal to 2 in general. What we do is we consider dividing a and b by m to give quotients and remainders, which we can always do by the division algorithm. So a has to be a quotient 1 times m plus a remainder, where the remainder is between 0 and m minus 1. And b can similarly be written as q2 times m, some other quotient, and some other remainder. If those remainders are equal to each other, we write this horrible symbol and say a is congruent to b modulo m. This is what we really mean by this horrible symbol, a mod b, or a is congruent to b mod m. If a and b leave the same remainder, r1 equals r2, when we divide them by m, we say that a and b are congruent modulo m, and we write this horrible symbol. Let's do some examples. All right, Alice is going to join us for a little bit. We're going to do congruence modulo 5. So let m equal 5 be the fixed number that we're going to divide everybody else by. And we're going to consider dividing every integer z, these guys, by 5. What we notice first is there's infinitely many numbers in the integer z, and there's only 5 possibilities, 0, 1, 2, 3, or 4, when we divide by 5. Therefore, every integer, no matter how large it is, we're going to play this game. In the next video, what we're going to do is we're going to try and divide horribly large powers of some base by some modulus m and find out what the remainder is. And we're going to play this black magic witchcraft to try and get there. But regardless of how large this number is, we know now when we divide by 5, there's only 5 remainders that we could leave, 0, 1, 2, 3, or 4. So let's try to find out in every number that we're given, they must be leaving the same remainder or congruent modulo one of the numbers between 0 and 4 when I divide by 5. Let's find out for each of these numbers. For 7, what we see is, what we want to do is, negative 7 specifically is going to be this time negative 2 times 5, which is negative 10, plus 3, because the remainder has to be between 0 and 4. So what that says is negative 7 is congruent to 3 modulo 5. Why is that? Well, because 3, if I look at 3 also, 3 is no groups of 5 plus 3, so he leaves his own remainder. So these two numbers, negative 7 and 3, leave the same remainder when I divide by 5. So negative 7 and 3 are congruent modulo 5. Another one that we want to do is, what we can consider is, what if I look at 0? Well, 0 is equal to, again, 0 groups of 5 plus 0. So 0 leaves its own remainder when I divide by 5. And in particular, 5 is one group of 5 plus 0. So 5 is congruent to 0 mod 5, which is also a good thing to know. M is always congruent to 0 modulo itself, m. So 5 is congruent to 0 mod 5. This is also a good thing to start looking at. For 9, what I want to consider now is, when I look at 9, I can get rid of this now. I don't need it. Are you kidding? Or no? You're just watching all the other stuff. And you're supposed to pay attention like the students. Okay, 9 is, now let's do this, one group of 5 plus 4. And I look at 4. 4 is 0 groups of 5 plus 4. So we notice from this that the remainders are the same, that 4 is congruent to 9 mod 5. When I look at, they have to leave the same remainder. When I look at 2021, maybe I have to do some long division with 2021. When I divide by 5, I'm going to get 4. I'll get 20, subtract 0, bring a 2 down. I'm going to get 0, brings down 21. I'll get a 4 again. We'll get 20, we'll get a 1. This says that 2021 is 404 groups of 5 plus a remainder of 1. So this says 2021 is congruent to 1 mod 5. 2021 and 1 leave the same remainder when I divide by 5. This is what we're talking about by measuring numbers congruent modulo 5. But every number, regardless of the number I pick, whether it's negative or large, positive, it doesn't matter. All these numbers have to be congruent to one of the numbers between 0 and 4, which is 5 minus 1. Let's call these things something and we'll give them notation. These are going to be congruence classes modulo 5. Okay, kitty. All right, so now what we're going to do is we're going to create these congruence classes modulo 5, and they're sets, and this is how we're going to denote them. They can have any representative in here. If you put brackets around that, that means the congruence class of everybody that leaves the same remainder as the person that's on the inside. So if I'm talking about the congruence class of 0, that's everybody that leaves a remainder of 0 when I divide by 5. Let's go through what that looks like. But we're categorizing integers because we want to know which integers are congruent or the same with the measure modulo 5. How are we going to do this specifically? Well, if I look at the congruence class of 0, I know that 0 is in there. And then if I look at 5 leaves a remainder of 0, any number that is a multiple of 5 is going to leave a remainder of 0 when I divide by 5. So that will be -5 and -10 ... Also, when I look at remainders that leave, or numbers that leave a remainder of 1 when I divide by 5, well, 1's going to be in there. And then actually it turns out the next theorem that we're going to do, which will relate these things to equality, is going to be just add multiples of 5 to the first number that's in the class. So 1 plus 5 is 6, plus 5 is going to be 11 ... And if we do 1 minus 5 will be -4, minus 5 again will be -9 ... Then when I look at 2, 2 is going to be in that class. 2 leaves its own remainder when I divide by 5. Then if I start adding 5, 7 and 12, all these numbers are going to leave a remainder of 2 when I divide by 5. But if I subtract off from 5, I'll get -3 and -8. All these numbers leave a remainder of 2 when I divide by 5. For 3, 3 definitely leaves its own remainder. Then if I start adding 5, I'm going to get 8, and then I'll get 13 ... Okay, he wants to go now. And then if I subtract off 5, I'll get -4, and then we'll get -9, or sorry, I went the wrong way, -2. 3 minus 5 is -2, minus 5 again will give me -7. These are all the numbers that leave a remainder of 3 when I divide by 5. And then every single number that leaves a remainder of 4 is going to be grouped as the 4. And then if I add a 5, I'll get a 9. And then if I add 5, I'll get 14. And I'm going to get these numbers. And if I subtract off, I'll get -1. And then we'll get -6 ... And what that shows us is, if we go through this now, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, all the numbers are there. And if we go the negative direction, yeah, 0, -1, -2, -3, -4, -5. All the numbers are there. So what we're going to say with this is, and we have results that we can say in number theory, that Z is the union of all of these congruence classes. Union 2, 3, union 4, and is empty for I not equal j in these from 1 to 4. So the Z is the disjoint union of its congruent classes modulo 5, because our M, remember, is 5. So this is what we mean. We can break every number and break them into categories or into sets modulo 5 or modulo any number M, essentially. This is going to be the idea. Now what we're going to do is give a couple results on how to use the black magic or modular arithmetic to get clever results. The next video specifically will do divisibility tests and doing this powers game dividing large powers of certain numbers by other numbers and trying to find the remainder. We'll play that black magic game. That black magic game specifically is going to be used to find divisibility tests for integers, because we use a base 10 representation. And then the other major application of this can be a window into cryptography and how we do solve the Enigma machine cipher specifically. So let's first do the main theorem, which is going to be relating congruences to divisibility. And because we can relate divisibility to equality, the main result of congruence modulo m says that two numbers are congruent modulo m if and only if their difference is divisible by m. Let's get to that. All right, theorem. Let m be a positive integer, which is at least 2, and let a and b be any integers. Then a is congruent to b modulo m if and only if m divides b minus a. Let's prove that, and then we'll do a remark on this relates congruence land to divisibility land, and because we have divisibility land, we can do divisibility land to equals land, and then we can relate congruences directly to equality, and then this is the way that you're going to want to prove a lot of things. First of all, proof. If, let's do this direction. If a is congruent to b mod m, then we know from the division algorithm a is congruent to b mod m, and a is equal to q1 m plus r, and b is equal to q2 m plus r, because we know the remainder is equal by the definition of congruent modulo m. Therefore, so we have technically an r1 and r2, but we know r1 equals r2 equals r, because we know a is congruent to b mod m. From that, now let's look at their difference then. What I want to look at, what we want to show is that b minus a is a multiple of m. Indeed, what we're going to get is this now says that if I look at b minus a, that is going to be q1m or q2m plus r minus q1m plus r. When we do that, we're going to get q2 minus q1 times m plus r minus r, which is going to go away to 0. And what that says is, this says that m divides b minus a. Conversely, if we're going to prove the other one, conversely, what we have is, what we're going to assume is that if m divides b minus a, then we know that b minus a equals m times q, because it has to be this. On the other hand, so b minus a is a multiple of m, but we also know if we're going to, we can always still do this as well. So on the other hand, we also have that b minus a is also going to equal q1 m1 plus r1 minus, sorry, this would be the 2 again, minus q1 m1 m plus r1. So this gives us what? This says that mq from this one, which is b minus a, also has to equal m q1 minus q2 plus r1 or r2 minus r1. I basically ran out of room. Let me move that up. What that tells me now is from here, what we get is, if I bring this to the other side, that says r2 minus r1 equals m times q1 minus q2 minus q. So I bring this one to the other side and then this one to the other side, so it should be r1 minus r2. Sorry, not that it matters, but there we go. What does that say? This says that m divides r1 minus r2, but 0 is less than or equal to r1, r2 is less than or equal to m minus 1. Both of these numbers are between 0 and m minus 1, so this says that r1 minus r2 has to equal 0 is the only way that works, and that says that r1 equals r2, and so a is congruent to b modulo m. This is the converse of the statement. Thus, what we have is a is congruent to b modulo m if and only if m divides their difference b minus a. This will be extremely useful when we do the remark. So let's get rid of this and write the remark. What we just saw was the theorem that we just had was A is congruent to B mod M if and only if M divides B minus A. But then we can also use, if we remember what that means about equality, that means that B minus A over M is an integer, some integer Q, say. So what that says is B has to equal A plus M times Q. This is extremely important. First of all, this is congruence land, which nobody likes. And then this is divisibility land, which nobody likes also. And then this is equality land, equals land. I don't want to call it equality land, that's something else probably. This is equals land. So we want to go from congruent land to divisibility land to equals land, where you're most familiar with and you've spent most of your time with. The theorem tells us we can go from congruence land to divisibility land, and then we know that we have a link between divisibility and equality. B divides A if and only if B or A over B is an integer. So that means there has to be some integer Q, and that says A is equal to Q times B. And this is where we get B minus A would be a multiple of M, but if we bring the A to the other side, we get this clever equality. What does this do for us? If I now take M equals 5, which was our running example for the modulus, let A be 37. If I now ask the question, find all other numbers B which are congruent to 37 modulo 5. Well, the way to do that is right here. B is going to be congruent to 37 if and only if B equals A 37 plus multiples of 5, where Q is any integer. This is what this is saying. Therefore, if I want to know what numbers B are congruent to 37, I have to add and subtract multiples of 5 to 37. Therefore, B, which is in the congruence class of 37, this will equal what? All the numbers, which when I add them, first of all, what am I going to get? 37 has to be in there. And then let's subtract, first of all, 37 minus 5 is going to be 32 is going to be in there. And then minus 5 is going to give me what? 27 again. And then subtract a 5, what am I going to get? I'm going to get 22, then we're going to get 17, and then we're going to get 12, and then we're going to get 7, and then we're going to get 2, and then we're going to get negative 3, dot, dot, dot. This is going to be all the numbers, and then you can keep going. These are all the numbers that are congruent to 37 modulo 5. This is how we find all the numbers. How do you find numbers in this black magic business of modular arithmetic modulo 5? To find any number and turn a 37 into what that says is 37 is congruent to negative 3 mod 5, because we now know that they're in the same congruence class. They all leave the same remainder when I divide by 5. Therefore, 37 is congruent to any one of these numbers in here. 37 is congruent to 32, which is congruent to 27, which is congruent to negative 3 modulo 5. This is how we compute these. Let's do one more result, and then next time we'll get into all the modular arithmetic and how to use these to find divisibility tests and to solve the Enigma machine. All right, for the last result of this video, what we're going to do is show that it's an equivalence relation, that congruence modulo M is essentially what we call an equivalence relation, which means it has these 3 nice properties, whether you call them these nice fancy names or not. What we want is let M be an integer which is at least 2, and let A, B, C be arbitrary integers. And then what we have is a number always leaves the same remainder as itself when I divide by M. This is clear, so A is always congruent to itself modulo M. This is called reflexivity. If A is congruent to B mod M, then we must have that B is also congruent to A mod M. This seems reasonable. If A and B leave the same remainder, we want B and A to leave the same remainder when we divide by M. And then transitivity is going to be if A and B are congruent mod M and B and C are congruent mod M, then we want A and C to be congruent modulo M. Let's prove, say, C. I'll leave 1 and 2 as an exercise to the viewer. Try these ones for yourself. What we're going to use is the previous theorem, the congruence divisibility theorem, which links this fact that this is true if and only if M divides B minus A. Let's erase this and get to it. So proof, what we have is if A is congruent to B mod M and B is congruent to C mod M, then we know from the theorem, the previous theorem, congruence divisibility, we know that M divides B minus A and M divides C minus B. And that says from the equality connection, we know that B minus A is equal to M times Q and C minus B is equal to M times P, say, for integers P and Q. Then what we want to look at is we want to look at C minus A. So cleverly from these two pieces of information, from this and this, I'm going to do this thing plus this thing. If I look at C minus B equals MP and B minus A equals MQ, and if we add these things, then what we're going to get is these middle ones will cancel and we'll get C minus A is equal to MP plus MQ. And what that tells me is C minus A is equal to MP plus Q. And what that says is M divides C minus A, and that's if and only if from our theorem, again, that C or A is congruent to C mod M. It's supposed to be an A. So if A is congruent to B mod M and C is congruent to, or B is congruent to C mod M, then we have that A is congruent to C mod M, so we do have transitivity. Please subscribe right here and hit the notification bell. I'm the Tutor Wizard. I'll see you next time. Next time, specifically, what we're going to do is we're going to look at this, more of these properties and modular arithmetic, and then we will find clever divisibility tests for numbers in base 10 representation, and we will give a way to crack the Enigma machine using congruence modulo M, modulo 26, specifically English letters of the alphabet. See you next time.